Tonight, we're going to put a number on the entire universe. How many galaxies are there? It's a question that sounds like it should have a clean answer, the way we know how many planets orbit the Sun or how many moons circle Jupiter. But here's what most people don't realize. Every galaxy you could ever count is just the ones bright enough to see. For each one our telescopes can pick out, there may be many more hiding in the dark, too faint to register, too distant to resolve, or buried behind the dust and glare of everything in between. By the end of tonight, you're going to understand how much of the universe we can truly see, how much stays hidden, and why most of the cosmos will eventually vanish from our view altogether. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Step outside on a clear, dark night, far from any city lights, and look up. If your eyes are good and the sky is truly dark, you might see a few thousand individual stars. That's it. A few thousand points of light scattered across the dome of the sky. Every single one of those stars belongs to our own galaxy, the Milky Way. Every star you have ever seen with your naked eye, every constellation you've ever traced, every shooting star, every planet, all of it lives inside this one structure. The faint band of pale light that arcs across a truly dark sky, the one that gave the Milky Way its name, that's not a cloud. That's the combined glow of hundreds of billions of stars, too far away to see individually, packed into the disk of our galaxy as we look toward its crowded center. For thousands of years, that band of light was simply a mystery. People told stories about it. They saw a river, a road, a trail of spilled milk across the heavens. But nobody knew what it was. And here's the remarkable part. With the naked eye alone, from a dark enough place, you can actually see other galaxies. You just don't realize it. If you're in the northern hemisphere and you know exactly where to look, on the very best nights, you can spot a small, faint, fuzzy smudge in the constellation Andromeda. It looks like nothing. A little blur, a flaw in the sky. That blur is the Andromeda Galaxy, and the light hitting your eye from that smudge has been traveling for about 2.5 million years to reach you. When that light left Andromeda, there were no modern humans on Earth. You are looking at the single most distant object visible to the unaided human eye. An entire galaxy of around 1 trillion stars. And to your eyes, it's nothing more than a faint grey stain. From the southern hemisphere, there are 2 more. 2 soft, glowing patches that look like detached pieces of the Milky Way. These are the Magellanic Clouds, 2 small galaxies that orbit our own. Sailors used them for navigation for centuries, without ever suspecting what they truly were. And that's essentially the limit of what we can see without help. A handful of fuzzy smudges. So you can perhaps understand why, for almost all of human history, we believed the Milky Way was everything. It wasn't arrogance. It was simply what the evidence showed. The Milky Way appeared to contain every star, and beyond its glow, there seemed to be only darkness. The whole story begins to change with the invention of the telescope. The very first clue came early, almost as soon as the telescope existed. When Galileo turned his crude little telescope toward that faint band of milky light arcing across the sky, he saw something that no human had ever seen before. The band was not a cloud of glowing vapor at all. It dissolved, under his lens, into countless individual stars, far too faint and too numerous to separate with the naked eye. The Milky Way, he realized, was made of stars. A vast multitude of them, blurred together into a single river of light by sheer distance. It was the first hint that the cosmos was deeper and more crowded than anyone had imagined. But the stars were only the beginning of the strangeness. When astronomers began turning telescopes toward the sky in the 1600s and beyond, they started noticing strange objects. Not points of light like stars, but soft, fuzzy, cloudy patches. They called them nebulae, from the Latin word for cloud. Some of these nebulae really were clouds of gas inside our galaxy, but others looked different. They had elegant spiral shapes, like whirlpools frozen in the dark, and nobody knew what they were. By the 1700s and 1800s, astronomers were cataloguing hundreds, then thousands of these mysterious spiral objects. One of the earliest catalogues came from a comet hunter named Charles Messier, working in the 1700s. He kept being fooled by these fuzzy patches, mistaking them for the comets he was searching for. So, in frustration, he wrote down a list of all the annoying smudges that were definitely not comets, so that he and others could ignore them. That list of cosmic nuisances, drawn up so they could be dismissed, turned out to contain some of the most magnificent objects in the entire sky, including the Great Spiral in Andromeda itself. The things he catalogued to avoid would, 2 centuries later, become the very objects that revealed the true scale of the universe. Around the same time, an astronomer named William Herschel, along with his sister Caroline, set out to do something even more ambitious. They tried to map the Milky Way itself, counting stars in different directions to work out its shape. Herschel slowly built a picture of our galaxy as a vast, flattened disk of stars, with our sun somewhere inside it. It was a brilliant achievement, and it gave humanity its first real sense of living inside a structure, rather than simply under a dome of fixed lights. But Herschel, like nearly everyone of his time, still assumed that this disk of stars was the whole of creation. The spiral nebulae remained a riddle no one could solve. And the riddle only grew sharper as telescopes improved. A fierce argument began to take shape, an argument that would last for over a century. What were the spiral nebulae? There were 2 competing answers, and the difference between them was nothing less than the difference between a small universe and an unimaginably large one. The first camp said the spiral nebulae were relatively small clouds of gas located inside our own Milky Way. In this view, the Milky Way was the entire universe, and these spirals were just features within it, like islands inside a single sea. The second camp had a far more radical idea. They suggested that the spiral nebulae were not inside the Milky Way at all. They proposed that each spiral was its own separate galaxy, a vast collection of billions of stars located impossibly far away, far beyond the edge of our own. They called these objects island universes. It was a beautiful and almost frightening idea. If it was true, then our galaxy was not the universe. It was just one island among countless others, floating in an ocean of space so vast that other entire galaxies were reduced to faint smudges. The argument came to a head in the 1920s. In 1920, 2 of the leading astronomers of the age stood up and publicly debated the question in what became famous as the Great Debate. On one side stood the argument that the universe was small and that the Milky Way was all of it. This side pointed to apparent evidence that the spiral nebulae were spinning and changing far too quickly to be enormous, distant galaxies. If a spiral were truly millions of light years across, they argued, it could never appear to rotate within a human lifetime, so it must be small and nearby. They also pointed to occasional flare-ups inside some spirals, sudden bursts of light, arguing that if these were ordinary exploding stars, then for them to appear as bright as they did, the spirals had to be relatively close. On the other side stood the argument for the island universes, the idea that the cosmos was filled with separate galaxies stretching out into the dark. This side noticed that the spiral nebulae were strangely absent from the band of the Milky Way itself, as though something in our galaxy's disk was blocking them from view, which made far more sense if they lay far beyond it. They argued that the occasional flare-ups, properly understood, were so luminous that the spirals must lie at tremendous distances to appear as faint as they did. Both sides were partly right and partly wrong, drawing reasonable conclusions from incomplete and sometimes misleading evidence. And here's the honest truth about that debate. Neither side could win, because nobody had the evidence. Nobody could measure how far away the spiral nebulae actually were. And without distance, the whole question was impossible to settle. If the spirals were close, they were inside the Milky Way. If they were unbelievably far, they were galaxies in their own right. Everything depended on distance. And measuring the distance to a faint, fuzzy spiral, millions of light years away, seemed completely beyond reach. The answer came from a man named Edwin Hubble, working with one of the largest telescopes in the world, perched on a mountain in California. In the early 1920s, Hubble was studying the Andromeda spiral, that same faint smudge you can see with the naked eye. And within it, he found a very special kind of star. These stars are called Cepheid variables, and they have an almost magical property. They pulse. They brighten and dim in a steady, regular rhythm, swelling and shrinking over days or weeks. And astronomers had discovered something extraordinary about them. The speed of a Cepheid's pulse is directly tied to its true brightness. A Cepheid that takes longer to pulse is genuinely, intrinsically brighter than one that pulses quickly. This is the key that unlocks everything. Because if you know how bright a star truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it must be. A bright candle that looks dim must be far away. A bright candle that looks brilliant must be close. Cepheids are like cosmic candles whose true brightness you can read directly from their rhythm. So Hubble found a Cepheid variable inside the Andromeda spiral. He watched it pulse. He measured its rhythm. He calculated its true brightness. And then he worked out the distance. The answer was staggering. Andromeda was not inside the Milky Way. It was nowhere near inside the Milky Way. It was hundreds of thousands of light years away, far beyond anything in our own galaxy. Today, we know the real figure is even larger, around 2.5 million light years. The spiral was its own separate galaxy, an island universe, exactly as the bold camp had predicted. In a single measurement, the universe exploded in size. Overnight, the Milky Way went from being everything to being one galaxy among many. And those thousands of other spirals that astronomers had catalogued, all those mysterious fuzzy patches, they weren't gas clouds within our galaxy. They were other galaxies. Thousands of them, each one a Milky Way of its own, filled with hundreds of billions of stars. It's hard to overstate what a shock this was. In the span of a few years, humanity learned that we were not living in the universe. We were living in one tiny corner of a cosmos filled with galaxies, stretching out as far as our telescopes could reach. And the obvious next question, the one that defines everything we're exploring tonight, immediately arose. If there are other galaxies out there, then how many are there? Are there hundreds? Thousands? Millions? Or something far beyond anything we could imagine? Edwin Hubble was not finished reshaping our picture of the cosmos. Having proven that the spiral nebulae were distant galaxies, he and others began measuring not just how far away those galaxies were, but how they were moving. And they found something astonishing. Almost every galaxy was rushing away from us. Not just a few of them, but nearly all of them, in every direction. And the further away a galaxy was, the faster it appeared to be fleeing. This relationship, that more distant galaxies recede more quickly, became one of the foundational discoveries of all of science. It revealed that the universe is not static and unchanging. It is expanding. The galaxies are not flying apart through space like debris from an explosion. Rather, space itself is stretching, and the galaxies are carried along with it, like raisins embedded in a loaf of bread that swells as it bakes, every raisin drifting away from every other. This single insight, that the universe is growing, would later lead, when run backward in time, to the idea that everything began from an unimaginably hot, dense state around 13.8 billion years ago. But for our question tonight, this discovery matters for another reason. The way a galaxy's light is stretched by the expanding universe, shifted toward longer, redder wavelengths, became a tool. By measuring how much a galaxy's light has been stretched, astronomers can estimate how far away it lies and how far back in time we are seeing it. This is part of what astronomers call the cosmic distance ladder, a series of overlapping techniques, each one reaching further than the last. The first rungs are nearby and direct. We measure the distances to close stars by watching them shift slightly against the background as Earth moves around the Sun. The next rung uses pulsing Cepheid stars, the same kind Hubble found in Andromeda, to reach across to nearby galaxies. Further out, where even Cepheids fade from view, astronomers use a special kind of stellar explosion, a particular type of supernova that always detonates with very nearly the same true brightness. Because these explosions always shine with a known intrinsic power, they act as brilliant beacons visible across billions of light years, and by comparing how bright they truly are to how bright they appear, we can measure staggering distances. And beyond even that, we lean on the redshift itself, the stretching of light, to gauge the most remote galaxies of all. Rung by rung, this ladder lets us climb out from our own backyard to the very edge of the visible cosmos. Without it, the question of how many galaxies exist could never even be approached. Because to count galaxies, you first have to know how far away they are, how much space they fill, and how far back in time you are looking. For decades after Hubble's discovery, astronomers had no real way to answer that. They could count the galaxies they could see, but their telescopes could only reach so far. The galaxies they could observe were just the bright, close ones. Beyond them lay an ocean of darkness, and nobody knew how full that darkness was. The breakthrough came in the 1990s, with a telescope that had been lifted above the Earth's atmosphere entirely, the Hubble Space Telescope, named in honor of the very man who proved other galaxies existed. And it came from one of the boldest, strangest decisions in the history of astronomy. The director of the telescope decided to do something that, on the surface, sounded almost wasteful. He decided to point this incredibly expensive, in-demand telescope at a patch of sky that appeared to be completely, utterly empty. A small, dark, unremarkable speck near the handle of the Big Dipper. A region with no known bright stars, no known galaxies, nothing. It looked like pure black nothing. The patch of sky was tiny. If you held a single grain of sand at arm's length up against the night sky, it would cover roughly the same amount of space as this target. And the plan was to stare at that one tiny dark grain of sky for 10 straight days, letting the telescope soak up every faint particle of light that drifted in from that direction. Many people thought it was a gamble, bordering on madness. What if there was nothing there? What if 10 days of one of humanity's most valuable instruments were wasted on a picture of empty blackness? The telescope opened its eye on that dark little patch and held its gaze for days, gathering the faintest whispers of ancient light. And then the image came back. That tiny patch of supposedly empty sky was not empty at all. It was crowded. It was teeming. In that single grain of darkness, the telescope had captured around 3,000 galaxies. 3,000. Not stars. Galaxies. 3,000 separate islands of stars, in a patch of sky so small it was almost nothing, a patch most astronomers had assumed was void. Some of them were spirals like our own. Some were vast glowing ellipticals. Some were strange, distorted, irregular shapes from the early universe. And many of them were so far away that their light had been traveling for billions of years before it finally landed on the telescope's detector. And this is the part that turns a photograph into a time machine. When you look at a galaxy whose light has traveled for 10 billion years, you are not seeing that galaxy as it is now. You are seeing it as it was 10 billion years ago, when that light first set out on its journey, long before the Earth or the Sun even existed. The deep field image was not just a picture of distant galaxies. It was a picture of the past, with the nearest galaxies showing recent times and the faintest, most distant smudges showing the universe as it was in its youth, all captured in a single frame. In one small rectangle of sky, the telescope had laid out billions of years of cosmic history, side by side. The reaction among astronomers was a mix of awe and disbelief. A patch of sky, chosen precisely because it looked empty, had turned out to be one of the most crowded, profound images ever taken. It settled, once and for all, the realization that had begun with Hubble decades earlier. The universe was not sparsely populated. It was densely, almost unimaginably full of galaxies, in every direction, as far as we could possibly see, and at every era of cosmic time. This image became known as the Hubble Deep Field, and it changed astronomy forever, because the logic was inescapable. If a patch of sky that small, in a direction that looked completely empty, contained 3,000 galaxies, then the entire sky must be carpeted with them. The darkness wasn't empty. The darkness was full. We had simply never looked deep enough to see it. Astronomers were not content to stop there. If staring for 10 days revealed 3,000 galaxies, what would happen if they stared even longer and even deeper? In the early 2000s, they did it again, but better. This time, they pointed the telescope at another tiny, dark patch of sky, this one in the southern constellation of Fornax, and they let it stare for the equivalent of many days, spread across months of observation. This image became known as the Hubble Ultra Deep Field, and in this single sliver of sky, smaller than a grain of sand held at arm's length, the telescope captured around 10,000 galaxies. 10,000. Many of them were so distant, and their light so ancient, that they appeared as they had existed when the universe was only a few 100 million years old, a tiny fraction of its current age. Then, a few years later, astronomers combined years of observations of that same region into an even deeper image, the extreme deep field, squeezing out the faintest, most distant galaxies yet, objects whose light had traveled for well over 13 billion years to reach us. There is also a remarkable trick that nature itself provides, helping us see galaxies that would otherwise be far too faint and distant to detect. According to our understanding of gravity, mass bends space, and light, traveling through bent space, follows a curved path. So when a truly massive object, like a great cluster of galaxies, sits between us and something far behind it, that cluster's gravity bends and focuses the light of the more distant object, acting like a giant natural lens in space. Astronomers call this gravitational lensing. By pointing their telescopes at massive foreground galaxy clusters, they can use the cluster's gravity to magnify and brighten the faint, distant galaxies hidden far beyond it. The light of those background galaxies is often smeared into strange arcs and streaks, warped by the lensing, but the magnification can make a galaxy hundreds of times brighter than it would otherwise appear. In this way, the universe lends us a hand, using its own enormous masses as lenses, to reveal some of the faintest, most distant galaxies we have ever glimpsed. Many of the earliest galaxies we know of were found precisely this way, their light bent and amplified by an intervening cluster, allowing us to peer further back than our telescopes could manage alone. Each time they looked deeper, they found more. And this is the pattern that defines the entire question of counting galaxies. There is no edge where the galaxies stop and the emptiness begins. Every time we build a more powerful instrument, every time we stare a little longer into the dark, more galaxies emerge from the shadows. So now, astronomers had a method. You take one of these deep field images. You carefully count every galaxy in it. You measure exactly how much of the sky that little patch covers. And then you do the multiplication. The full sky is enormous compared to one of these tiny patches. To cover the entire sphere of the sky with patches the size of the ultra-deep field, you would need to tile that image millions of times over. So, you take the number of galaxies in your patch, and you multiply it by how many of those patches it would take to wrap the whole sky. And when astronomers did that calculation, they arrived at the first serious, modern answer to our question. The observable universe, they estimated, contained somewhere between 100 billion and 200 billion galaxies. Let that settle for a moment. 100 billion to 200 billion galaxies. Not stars, galaxies. And remember, each one of those galaxies holds, on average, somewhere between a few billion and a few hundred billion stars of its own. For a long time, this was the number you would read in textbooks and hear in documentaries. Roughly 200 billion galaxies. It's a number that already shatters the imagination. If you tried to count 200 billion galaxies, naming one every single second without ever sleeping, eating, or stopping, it would take you longer than the entire age of the universe to finish. You would never even come close. And yet, this number, as staggering as it is, turned out to be only the beginning. Because there was a problem hiding inside it. The deep field images were extraordinary, but they had a limit. They could only show galaxies that were bright enough and close enough for their light to register on the detectors. The faintest, smallest, most distant galaxies simply didn't show up. Their light was too feeble, smeared out across too much space and too much time to leave any mark at all. So the 200 billion figure wasn't really the total number of galaxies. It was the number of galaxies we could see. And those are not the same thing. In the year 2016, a team of astronomers, led by a researcher named Christopher Consolis, set out to solve this problem properly. They didn't just count the galaxies in the images. They asked a deeper question. How many galaxies must be out there that we cannot see? To answer that, they did something clever. They took the deep field images and converted them into three-dimensional maps, sorting the galaxies not just by position in the sky, but by distance and therefore by time. Because looking far away in space is the same as looking back in time. The further out you look, the younger the universe you are seeing. And what they found was revealing. When they looked at the early universe as it was billions of years ago, they found that it was packed with small galaxies. Far more small galaxies, crowded together, than exist in the same volume of space today. This made sense, because over cosmic history, galaxies merge. Small galaxies collide and combine into larger ones again and again, so the early universe had vastly more individual galaxies than the universe we see around us now. By studying how the number of galaxies changed across cosmic time, and by using mathematical models of how galaxies form and grow, the team could estimate the entire population, including all the small, faint galaxies hidden below the reach of our telescopes. And the conclusion was breathtaking. They calculated that for the observed numbers to make sense, there had to be far more galaxies than anyone could currently see. In fact, they concluded that at least 90% of all the galaxies in the observable universe are too faint and too far away to be detected with present-day telescopes. 90% of all galaxies, completely invisible to us, hidden in the dark, below the threshold of every instrument we've ever built. When they added those invisible galaxies to the ones we can see, the total number leapt upward by a factor of 10. The new estimate was not 200 billion galaxies. It was around 2 trillion. 2 trillion galaxies in the observable universe. That is 2,000 billion. A 2, followed by 12 zeros. To even attempt to grasp it, imagine that every single galaxy were a grain of sand. 2 trillion grains of sand would fill enormous containers, vast piles, an amount of sand you could not count in 1,000 lifetimes. And each of those grains is not really a grain at all. Each one is an entire galaxy, hundreds of billions of stars, countless worlds, perhaps countless living things, all compressed in our minds into a single point. The number 2 trillion became the new headline answer. It spread through documentaries, articles, and textbooks. The universe, it seemed, was 10 times more crowded than we had ever dared to imagine. There was an important subtlety buried in that figure, though. The 2 trillion count included galaxies from across all of cosmic history, gathered into a single tally. But as we've seen, galaxies merge over time. Many of the small galaxies counted in the distant, early universe have, in the billions of years since, already collided and combined into larger galaxies. So, the number of galaxies that exist in the universe right now, at this present moment, is almost certainly smaller than the total counted across all epochs. The 2 trillion was, in a sense, a count of every galaxy that has ever shone within our horizon, not a snapshot of how many are out there today. It was a profound and careful piece of work. But even as it spread through the world as the new headline number, the ground was already shifting beneath it. But science is never finished. And the story of counting galaxies took a sharp and surprising turn, because a few years later, a completely different method produced a completely different answer. The new evidence came from one of the most distant spacecraft humanity has ever launched, a probe called New Horizons. This was the spacecraft that flew past Pluto and sent back the first close-up images of that distant frozen world, before continuing on, out past the edge of the planetary system, into the deep dark of the outer solar system. And out there, New Horizons had a unique advantage. Here on Earth, and even close to the Sun, space is not truly dark. It's filled with a faint haze of scattered sunlight, bouncing off the countless tiny dust particles that drift throughout the inner solar system. This faint glow is called zodiacal light, and it pollutes every attempt to measure the true darkness of the sky. But New Horizons was far, far beyond all of that. It was out in a region so remote that the sun was just a bright star, and the dust haze of the inner system was left far behind. For the first time, a camera was sitting in genuine, profound darkness. To appreciate why that matters, you have to understand just how delicate this measurement is. The leftover glow from all the unseen galaxies in the universe is extraordinarily faint, far dimmer than the light of any single visible object. To detect it, you must first account for and remove every other source of light: the glow of nearby stars, the haze of dust, the scattered light of our own galaxy, the faint shine of everything in the foreground. Near Earth, the inner solar system's dust haze alone is brighter than the signal you're hunting for, drowning it out completely. Only from the deep outer reaches, far from that haze, could a camera hope to measure the true, faint background of the cosmos and isolate the glow of the galaxies we cannot see. So the team had a once-in-a-generation opportunity, an instrument sitting in the darkest place humanity had ever measured from. So the team used New Horizons to do something simple but profound. They measured the total amount of light coming from the sky. Not from individual galaxies, but the overall background glow. The combined light of every galaxy in the universe, seen and unseen, faint and bright, all blended together into a single dim, all-encompassing wash of light across the cosmos. The logic was elegant. If the universe really contained 2 trillion galaxies, then all those galaxies, even the invisible ones, would still be emitting light. And all that light would add up. It would create a measurable background glow. If there were 2 trillion galaxies, that background glow should be bright. If there were only a couple 100 billion galaxies, the glow should be much dimmer. So they measured the glow, subtracted everything they could account for, and looked at what was left over. And the answer surprised everyone. The leftover glow from unseen galaxies was small, much smaller than 2 trillion galaxies would produce. In fact, the measurement suggested that if you took all the galaxies that telescopes can directly see and simply doubled that number, you would have very nearly all the galaxies that exist. Not 10 times more. Just about twice as many as we can already see. That pointed back toward a number much closer to the original estimate. Somewhere around a few 100 billion galaxies, perhaps 200 billion, maybe a little more. Not 2 trillion. So, which is it? A couple 100 billion or 2 trillion? This is where the honest answer becomes the most interesting part of the whole story. The truth is, as of right now, we do not know. The 2 trillion figure comes from extrapolating models of tiny, faint galaxies we cannot see, and asking how many must be there to explain the patterns we observe across cosmic time. The few 100 billion figure comes from measuring the actual total brightness of the sky, and finding less hidden light than 2 trillion galaxies would require. Both methods are clever. Both rely on assumptions. And the gap between them is enormous, a factor of 10. Some recent analyses have even pushed the upper end higher still, suggesting that when you account for the very smallest, dimmest galaxies in just the right way, the number could climb past 2 trillion toward even larger figures. So the genuine current answer to how many galaxies exist in the observable universe is not a single clean number. It's a range. A range that stretches from a couple hundred billion at the low end to 2 trillion or more at the high end. And sitting with that uncertainty, accepting that we genuinely don't know whether the true number is 200 billion or 2,000 billion, is one of the most honest and humbling things in all of science. Think about what that uncertainty really represents. The gap between the two answers is not a small rounding error. It's a factor of 10, an entire order of magnitude between the lowest serious estimate and the highest. The difference between those two numbers is, all by itself, larger than the total number of galaxies anyone imagined existed for most of the 20th century. And the reason for the gap comes down to the same haunting fact at the center of this whole story. The galaxies we can see may be only a small fraction of the galaxies that exist. If the higher estimates are right, then for every galaxy our telescopes have ever detected, there could be 9 more hidden in the dark. Too faint and too distant for any instrument we currently possess. We would be like someone standing at the edge of a vast city at night, able to see only the few nearest, brightest windows, and forced to guess at how many darkened homes stretch away into the gloom. The lights we can count are real, but the darkness between and beyond them may hold the overwhelming majority of everything that's out there. To accept that, to hold a question this enormous and admit that our best answer spans a factor of 10, is not weakness. It is exactly what makes the question worth asking. To understand why this is so difficult, why we can't simply count them, we have to confront the strange and beautiful obstacles that stand in our way. The first obstacle is the most fundamental of all. We can only see a part of the universe. Not because our telescopes aren't good enough, but because of the nature of light itself and the age of the universe. The universe is around 13.8 billion years old. That means light has only had 13.8 billion years to travel since the very beginning. And light, fast as it is, has a speed limit. It travels at about 186,000 miles every single second, and nothing can travel faster. So there's a horizon out there in space, a boundary defined not by anything physical, but by time. Light from beyond that boundary simply hasn't had enough time to reach us yet. We call everything inside that boundary the observable universe. Everything beyond it is, for now, completely invisible to us and may always be. Here's where it gets stranger. You might expect that if the universe is 13.8 billion years old, the observable universe must be 13.8 billion light-years in radius. But it isn't. It's much larger. Because while that ancient light has been traveling toward us, space itself has been stretching, expanding, carrying distant galaxies ever further away. So the galaxies whose ancient light is only now arriving have, in the time since, been swept much further out. When you account for that expansion, the observable universe turns out to be about 93 billion light-years across from one side to the other. A sphere 93 billion light-years wide, centered on us, simply because we have to be somewhere, and this is where we happen to be. And there's a strange truth hidden inside this. We can never see any distant galaxy as it is right now. The light reaching us tonight from a galaxy a billion light-years away left it a billion years ago, so we see it as it was then, not as it is in this moment. The most distant galaxies we observe, we see as they were in the infant universe when they were just forming. What those galaxies look like today, whether they still exist as separate galaxies at all, or have long since merged into something else, we have no way of knowing, and never will. The distant universe is forever a record of the past, frozen in the light that has finally reached us. We are always looking backward, never at the present, and the further we look, the deeper into history we see. Every galaxy we count lives inside that sphere. And every estimate, the 200 billion, the 2 trillion, all of it, applies only to that sphere, only to the observable universe, only to the part we can, in principle, see. The second obstacle is what galaxies actually are, because they refuse to be simple. When you hear the word galaxy, you probably picture something grand and majestic, a great glowing spiral like our own Milky Way, or like Andromeda, with sweeping arms full of brilliant stars. And those galaxies certainly exist. The Milky Way holds somewhere between 100 billion and 400 billion stars. Andromeda holds around 1 trillion. Some of the giant elliptical galaxies, the truly enormous ones at the hearts of great galaxy clusters, can hold tens of trillions of stars, dwarfing our own galaxy completely. Galaxies come in a remarkable variety of shapes, and astronomers long ago began sorting them into families. There are the spirals, like our own Milky Way, and like Andromeda, with a central bulge of older stars surrounded by a flat rotating disk where graceful arms sweep outward. Lit by the blue glow of young, newly formed stars and the pink shimmer of gas clouds where new stars are still being born. Many spirals, including ours, have a straight bar of stars cutting across their centers, with the arms trailing off from the ends of the bar. Then there are the ellipticals, which look nothing like the elegant spirals. Ellipticals are smooth, featureless blobs of stars, ranging from nearly spherical to stretched out like a rugby ball, containing mostly old, reddish stars, with little gas left to form new ones. The largest ellipticals are the true giants of the cosmos, often found lording over the centers of massive galaxy clusters, having grown enormous by devouring smaller galaxies over billions of years. Between these two families sit lens-shaped galaxies, which have a disk like a spiral but no real arms, as though they were once spirals that used up their gas and faded. And then there are the irregulars, galaxies with no clear shape at all, often small, chaotic, and rich in gas. Sometimes twisted into strange forms by the gravitational pull of a passing neighbor. This whole classification scheme, sorting galaxies by their shape, was first laid out by Edwin Hubble himself, and astronomers still use a version of it today. But the grand, photogenic galaxies that fill our textbooks and our imaginations are, in truth, the exception rather than the rule. But here's the truth that complicates everything. The vast majority of galaxies are nothing like the Milky Way. Most galaxies in the universe are dwarf galaxies, small, faint collections of perhaps a few million to a few billion stars. Compared to the great spirals, they are tiny, dim, and easy to miss. And there are far, far more of these little dwarf galaxies than there are giant ones. So when you ask how many galaxies exist, you immediately run into a problem of definition. What even counts as a galaxy in the first place? Astronomers generally describe a galaxy as a large, gravitationally bound collection of stars, gas, dust, and dark matter, held together by its own gravity and bound up within a halo of that invisible dark matter. That dark matter halo is part of what separates a true galaxy from a mere star cluster, a simple group of stars with no such halo around it. But out at the faint, small end of the scale, this distinction becomes genuinely hard to apply. How small can a clump of stars be before it stops being a galaxy? There are objects out there that sit right on the boundary, small clusters of stars that might be the faintest dwarf galaxies, or might just be loose collections of stars that don't quite qualify. The line is genuinely blurry. And because the smallest galaxies are also the faintest and the most numerous, the answer to how many galaxies exist depends heavily on exactly where you draw that line. Count only the bright, obvious galaxies, and you get one number. Count every faint little dwarf you can possibly justify, and the number balloons. This is a huge part of why the estimates vary so wildly. The universe didn't build galaxies in neat, countable units. It built a continuous spectrum, from titanic ellipticals holding tens of trillions of stars, all the way down to faint smudges that barely deserve the name. Consider the extremes of that spectrum for a moment. At the largest end sit the supergiant elliptical galaxies found at the centers of the richest galaxy clusters. The most massive of these can stretch across millions of light years, many times the width of the Milky Way, having grown bloated over billions of years by swallowing every smaller galaxy that strayed too close. A single one of these monsters can contain the equivalent of tens of trillions of suns, a population of stars so vast it dwarfs entire small clusters of galaxies. At the opposite end sit the dwarf galaxies, and especially the faintest of them, the ultra-faint dwarfs. Some of these are so dim and so sparse that they contain only a few thousand or a few 100,000 stars, scattered loosely through a halo of dark matter. They produce so little light that we have only discovered them recently, lurking around our own Milky Way, almost invisible, even though they sit on our cosmic doorstep. If galaxies this faint exist all around us, just barely detectable, then the universe must be littered with countless others like them, far too dim ever to be seen across the vast distances of intergalactic space. And there are even stranger objects, sprawling galaxies as wide as the Milky Way, but containing so few stars that they are nearly transparent. Ghostly structures you could almost see straight through. This enormous range, from blazing giants to nearly invisible ghosts, is exactly why putting a single number on the galaxy population is so maddeningly difficult. The third obstacle is time itself, and the way the universe refuses to hold still while we count it. When you look at a distant galaxy, you are not seeing it as it is now. You are seeing it as it was when its light left it, perhaps billions of years ago. The further out you look, the further back in time you see. And the early universe was a very different place. In the first few billion years, the cosmos was smaller, denser, and absolutely swarming with small galaxies, far more than exist today. Over billions of years, those small galaxies have been crashing into each other and merging, building up into the larger galaxies we see in our local part of the universe. The Milky Way itself is the product of many ancient mergers, having swallowed smaller galaxies over and over throughout its long history. And this process is not finished, not even for us. Our great neighbor Andromeda is drifting toward us, and over billions of years to come, the two giant galaxies are expected to fall together and merge into a single larger galaxy. When that happens, where there were once two great spirals, there will be one. The count of galaxies in our own small corner of the universe will tick downward by one, as two become one. This is happening everywhere, all the time, across the cosmos, galaxies merging and combining, the total number slowly falling as the universe ages. So here is the deep, complication. When you count galaxies in a deep field image, you are counting galaxies from many different eras of cosmic history, all at once. Some of the galaxies you count in the distant, early universe have, in the time since, already merged together into single larger galaxies. The number of galaxies that existed in the early universe is not the same as the number that exist right now. In fact, the count has been steadily falling over cosmic time as mergers reduce many small galaxies into fewer large ones. So, when someone asks, how many galaxies exist, you almost have to ask in return, exist when? In the early universe. Today, averaged across all of cosmic history, which is what our images actually capture. There is no single moment we can point to. The universe we observe is a layered tapestry of every era stitched together, and counting it cleanly is like trying to take a single census of a population that is constantly merging and changing across billions of years. And there is a fourth obstacle, closer to home, and rather ironic. Our own galaxy gets in the way. The Milky Way is a flat disk of stars, gas, and dust, and we are sitting right inside it. When we try to look out at the rest of the universe, a large portion of the sky is blocked by the dense, dusty band of our own galaxy's disk. The dust and the crowds of foreground stars absorb and scatter the light of anything behind them, hiding whole regions of the distant universe from view. Astronomers call this blocked region the zone of avoidance, because it's the part of the sky where extragalactic surveys have to give up, unable to see through our galaxy's own clutter. For a long time, we simply could not know how many galaxies lay hidden behind the band of the Milky Way in that obscured strip across our sky. There is also the constant problem of confusion. When you look at a deep image, not every point of light is a distant galaxy. Some are foreground stars within our own galaxy, sitting between us and the depths beyond. Some faint smudges might be a single galaxy, or might be two galaxies so close together that they blur into one. Telling all of these apart, sorting the true distant galaxies from the foreground stars and the overlapping blurs, is painstaking, uncertain work. Every one of these difficulties, the obscuring dust, the foreground stars, the merging galaxies, the faint invisible dwarfs, the limits of our horizon, stacks on top of the others. And together, they explain why a question as simple to ask as how many galaxies exist remains, even now, one of the hardest in all of astronomy to truly pin down. To really appreciate what we're counting, it helps to understand how galaxies came to exist in the first place. Because galaxies were not always here. In the beginning, after the universe burst into existence and cooled from its initial searing heat, there were no galaxies at all. There were no stars. There was only a near uniform fog of hydrogen and helium gas, spread almost perfectly smoothly through an expanding, darkening cosmos. For a long stretch of time, astronomers call this period the Cosmic Dark Ages, because there was no starlight anywhere. The universe was dark, formless, and cold. But it was not perfectly smooth. There were the faintest ripples in the density of that early gas, tiny regions that were ever so slightly denser than their surroundings. We can actually see the imprint of those ripples today. When the universe was very young, it was so hot that it glowed, filled with light that could not travel freely through the dense fog of charged particles. As the cosmos expanded and cooled, that fog cleared, and the light was set free to travel across space. That ancient light is still arriving, stretched by billions of years of expansion into a faint hiss of microwaves coming from every direction in the sky. Astronomers call it the cosmic microwave background, and it is the oldest light we can ever see, a snapshot of the universe as it was long before any star existed. And mapped across that ancient glow are tiny variations, faint patches, very slightly warmer or cooler than their surroundings. Those patches are the seeds. They are the original ripples, the slightly denser regions from which all the galaxies would eventually grow. When we look at the cosmic microwave background, we are looking at the blueprint of the cosmic web, the faint pattern of lumps that gravity would spend billions of years sculpting into the trillions of galaxies we now try to count. And woven invisibly through everything was dark matter, that mysterious substance we cannot see but whose gravity shapes the entire cosmos. Dark matter does not give off light, does not interact with ordinary matter except through gravity, and outweighs all the ordinary matter in the universe by several times. In those slightly denser regions, dark matter began to clump together under its own gravity, forming invisible scaffolding, vast collapsing halos that would become the cradles of everything to come. Ordinary gas, drawn by the gravity of these dark matter halos, flowed downhill into them, pooling and compressing in their centers. As the gas grew denser and hotter, the very first stars finally ignited, blazing into life and ending the long darkness. These first stars were unlike any star today, enormous and brilliant, built only from the simplest elements, burning fast and ending quickly, forging heavier elements in their cores and scattering them outward. As the first stars and the first galaxies switched on, their fierce light began to transform the universe around them. The neutral hydrogen fog that filled all of space was gradually broken apart by this flood of starlight, in a great turning point that astronomers call reionization. Bubbles of cleared, transparent space grew around the first galaxies, slowly merging together until the whole universe became transparent, and starlight could travel freely across the cosmos. This was the dawn of the universe we recognize, a cosmos lit by galaxies, with clear space between them through which we can now look back and see them. The earliest galaxies were the ones that did this, the ones that ended the long darkness and cleared the cosmic fog. And those are precisely the galaxies that sit right at the edge of what we can detect, the faint, distant pioneers whose discovery tells us how and when the lights first came on. As more and more gas and stars gathered within the dark matter halos, the first true galaxies assembled, small and chaotic at first, glowing islands of newborn stars embedded in their invisible halos. And then those small galaxies began to do what they have done ever since. They pulled on each other. They collided. They merged. A small galaxy would fall into a larger one and be torn apart and absorbed, adding its stars to the growing structure. Again and again, over billions of years, small galaxies built up into larger ones, in a slow, relentless process of cosmic assembly. Every large galaxy we see today, including our own Milky Way, is the end result of countless such mergers. A grand structure stitched together from the remains of many smaller galaxies that came before. So, when we count galaxies, we are counting snapshots of this process, frozen at every stage, scattered across all of cosmic time. From the first faint clumps to the great spirals and giant ellipticals of the present day. And it is the earliest of these stages, the very first galaxies forming in the dark, that we most desperately want to see, because they hold the secrets of how everything began. For a long time, those first galaxies were utterly beyond our reach. Their light was too faint, too distant, and too stretched by the expansion of the universe for any telescope to capture. until, at last, we built one that could. Now, let's turn to the telescope that has thrown all of this into beautiful chaos and revealed an early universe that nobody expected. For decades, the Hubble Space Telescope was our deepest eye on the cosmos. But Hubble had a fundamental limitation. When you look at the most distant galaxies, their light has been stretched by the expansion of the universe. This is called redshift. As space expands, it stretches the wavelength of light traveling through it, shifting visible light toward the red end of the spectrum, and then beyond, into the infrared, where the human eye and ordinary telescopes cannot follow. The most distant galaxies of all have their light stretched so dramatically that all of it, every last bit, has been shifted out of the visible range entirely and into the infrared. Hubble simply couldn't see far enough into the infrared to capture them clearly. So, a new telescope was built, an instrument designed specifically to see the infrared light of the most ancient, most distant galaxies in existence. The James Webb Space Telescope. Launched at the very end of 2021 and parked far beyond the Moon, it is the most powerful space telescope ever built, with a golden mirror far larger than Hubble's, and detectors tuned exquisitely to catch the faint infrared whispers of the early universe. And almost immediately, it began breaking records and breaking expectations. Astronomers had models predicting what the early universe should look like. They expected the first galaxies to be small, faint, dim, and rare, just barely beginning to form in the first few 100 million years after the beginning. Instead, the new telescope found galaxies that were brighter, larger, and more developed than anyone thought possible at such an early time. It found galaxies that appear to have formed astonishingly quickly, far faster than the models suggested they could. It pushed the frontier back and back, finding galaxy after galaxy in eras of cosmic history we had never been able to glimpse before. It found a galaxy known as Jades, GSZ-14, which we see as it existed only about 290 million years after the beginning of the universe, when the cosmos was just 2% of its current age. And then, it broke its own record again. It found a galaxy called MOMZ-14, confirmed as the most distant galaxy ever observed, its light stretched by an enormous factor, showing us the galaxy as it existed a mere 280 million years after the beginning. 280 million years. In the lifetime of a universe that is 13.8 billion years old, that is the blink of an eye. The cosmos had barely begun, and already there were galaxies blazing with light. And these early galaxies were strange. They were more compact, brighter, and more chemically mature than the models predicted. They contained elements that should have taken longer to form. It was as though stars and galaxies had switched on far earlier and far more vigorously than our theories allowed. There were other surprises too. The new telescope found galaxies in the early universe that appeared to be far more massive, far more grown up than they had any right to be, so soon after the beginning. Some of these early galaxies seemed to contain as many stars as mature galaxies do today, even though the universe was only a few 100 million years old, leaving astronomers baffled as to how so many stars could have formed so quickly. And it found a strange new population of objects, small, intensely red points of light scattered across the early universe, which astronomers have nicknamed the little red dots. Nobody is entirely sure what they are. They might be unusually compact, early galaxies bursting with stars, or they might be the glow of rapidly feeding black holes in the infant universe, or something stranger still, that we have not yet understood. They were not predicted, and they do not fit neatly into our existing picture. The astronomers who built these models were not disappointed. They were thrilled, because this is what discovery actually looks like. It looks like finding something you did not expect, something that breaks your assumptions and forces you to think harder. There is now what researchers describe as a growing gap between theory and observation in the early universe. The first galaxies appeared sooner, shone brighter, and grew faster than we believed was possible. And every one of those early galaxies that we keep finding adds to the count and reminds us that the deep, early universe was already full of these glowing islands of stars. Far more of them than we ever expected to see. What this means for our grand question is profound. The more deeply we look, the more galaxies we find, and the more we realize how incomplete our count has always been. Every new telescope reveals galaxies that the previous generation of instruments was completely blind to. There is every reason to believe that whatever number we settle on today, future instruments will reveal more. And those instruments are already coming. A new generation of space telescopes is being built and launched to survey the sky far more widely than the James Webb Space Telescope can, capturing enormous fields of view and charting vast numbers of galaxies in a single sweep, sharpening our senses of the cosmos. On the ground, astronomers are constructing a new class of enormous telescopes with mirrors tens of feet across, far larger than anything that has come before, capable of gathering faint ancient light with unprecedented power. These extremely large telescopes will be able to study the early galaxies in detail, measuring what they are made of and how they are growing, where today we can barely detect them as points of light. Each new instrument peels back another layer of the dark, finding galaxies that were invisible to everything before it. This is the pattern that has held true at every single step of this story, from Galileo's first glimpse to the deep field images, to the golden eye of the James Webb Space Telescope. The closer we look, the more there turns out to be. And there is no sign, anywhere, that we have reached the bottom of it. There's another way that distant galaxies announce themselves across the cosmos, and it involves the monsters that lurk at their centers. At the heart of nearly every large galaxy, including our own, sits a supermassive black hole, an object containing the mass of millions or even billions of suns, crushed into a region of warped space from which not even light can escape. Most of the time, these black holes are quiet, slumbering at the cores of their galaxies. But when a black hole is actively feeding, when gas and stars spiral inward toward it, that infalling material is heated to ferocious temperatures and blazes with light before it disappears. The result is one of the most luminous objects in the entire universe, a quasar. A single feeding black hole at the center of a distant galaxy can outshine all the hundreds of billions of stars in that galaxy combined. Quasars are so brilliant that we can see them across almost the entire observable universe, beacons shining from galaxies so far away that their ordinary starlight would be far too faint to detect. In this way, the most extreme galaxies, the ones with the most active hearts, light their own way across the cosmos and let us find them at distances that would otherwise be impossible. Studying these distant beacons has taught us that supermassive black holes and galaxies grow up together, intertwined, each one shaping the other across cosmic history. And because quasars are so luminous, they serve another quiet purpose in the great census of the cosmos. When astronomers find a quasar blazing from the early universe, they have found, by definition, a galaxy. a galaxy so distant and so faint that, without its feeding black hole, it might have stayed hidden from us forever. Each quasar is, in effect, a galaxy holding up a lantern, announcing its presence across billions of light-years of empty space. The most distant quasars we have found shine to us from a time when the universe was less than 1 billion years old, their light having traveled for more than 12 billion years to reach our telescopes. And here lies one of the deepest puzzles in all of astronomy. For a black hole to grow massive enough to power a quasar, it normally needs a very long time to feed and to swell. Yet these early quasars, glimpsed when the cosmos was still in its infancy, already contain black holes with the mass of billions of suns. How did they grow so large, so quickly, when the universe had barely begun? It is a question we still cannot fully answer, and every new distant quasar that we count deepens the mystery rather than resolving it. What it tells us, though, is profound. It tells us that galaxies, and the monstrous engines at their cores, were assembling themselves astonishingly early, far earlier than we once believed possible. And it suggests that the great cosmic tally of galaxies stretches back almost to the very first moments when structure could exist at all. Every quasar we map is another data point, another distant island of stars confirmed, another faint thread woven into our slowly emerging picture of just how crowded the early universe truly was. It's a reminder that a galaxy is not just a passive collection of stars. It's a living, evolving structure with a powerful engine at its core, capable of flooding intergalactic space with light. While the great telescopes peer deep at individual patches of sky, another kind of effort has been quietly transforming our picture of the cosmos. Instead of staring very deeply at one tiny spot, astronomers have launched vast surveys that map huge swaths of the sky, charting the positions and distances of millions upon millions of galaxies. One of the first great efforts of this kind spent years systematically photographing the sky and measuring the distances to over 1 million galaxies, building the first truly large, three-dimensional map of our cosmic surroundings. That map revealed, for the first time, in full detail, the great cosmic web, the filaments and clusters and vast empty voids that structure the universe on the largest scales. More recent surveys have grown more ambitious still. A project designed to probe the nature of the universe's expansion has been measuring the distances to tens of millions of galaxies, using thousands of tiny robotic fibers that capture the light of thousands of galaxies at once, building the largest three-dimensional map of the cosmos ever made. And a dedicated space telescope has begun surveying enormous regions of the sky from beyond the Earth, with the explicit goal of charting the shapes and positions of well over 1 billion galaxies in order to study the mysterious dark energy driving the universe apart. These surveys do not see the faintest, most distant galaxies that the deep field images capture, but they do something just as important. They reveal the architecture of the universe, the grand pattern into which all those galaxies are woven, and they give us the statistics we need to estimate how galaxies are distributed across all of space. Every one of these maps, with its millions of glittering points, is humanity slowly filling in the census of the cosmos, one region at a time. And every one of them confirms the same humbling truth. No matter where we look, in every direction, the universe is filled with galaxies, scattered across the void in numbers that climb beyond comprehension. Let's pause to consider what all of this means when you multiply it out. First, hold in your mind the scale of just one galaxy. Our Milky Way is so large that light, moving at 186,000 miles every second, takes around 100,000 years simply to cross from one side of it to the other. Within that span live somewhere between 100 billion and 400 billion stars, and around a great many of them, planets. Every star you have ever seen, every story humans have ever told about the night sky, fits inside this single galaxy. And this one galaxy, vast beyond all human experience, is just one of the points we are trying to count. Now multiply. Take even the conservative estimate of a couple 100 billion galaxies. Now consider that an average galaxy contains, very roughly, around 100 million to a few 100 billion stars, with most galaxies being small dwarfs on the lower end of that range. When you multiply the number of galaxies by the average number of stars in each, you arrive at a figure for the total number of stars in the observable universe. And that figure is almost beyond language. The number of stars in the observable universe is estimated to be somewhere in the range of a number written as a 1 followed by 22 zeros, perhaps even a 1 followed by 24 zeros. There is a comparison that astronomers love to make about this, and for once it is genuinely accurate rather than just dramatic. The number of stars in the observable universe is thought to be larger than the number of grains of sand on every beach and in every desert on the entire planet Earth. Every grain of sand on every shore, in every dune, across the whole world. There are more stars than that. And each of those stars sits inside one of these galaxies we are trying to count. And around a great many of those stars orbit planets, worlds of rock and ice and gas, some of which may have oceans, atmospheres, and perhaps, on a tiny fraction of them, something stirring that we would recognize as life. When you hold the question of how many galaxies exist alongside the question of what each galaxy contains, the scale stops being a number at all. It becomes something closer to a feeling, a vertigo of the mind, standing at the edge of a quantity too large to hold. This staggering abundance leads naturally to one of the most haunting questions we can ask. If there are hundreds of billions, perhaps trillions of galaxies, and each one contains hundreds of billions of stars, and a great many of those stars host planets, then the number of worlds in the observable universe is almost beyond meaning. We now know, from decades of patient searching, that planets are not rare. Most stars seem to have planets of some kind, and a meaningful fraction of those planets orbit at distances where liquid water could, in principle, exist on their surfaces. When you fold all of this together, the number of potentially life-friendly worlds across all those galaxies climbs into figures so vast that they defy intuition entirely. And yet, despite all of this, we have so far found no clear sign of life anywhere beyond our own planet. This is the strange and unresolved tension at the heart of modern astronomy. The universe appears to be overflowing with the raw ingredients for life, with countless worlds in countless galaxies, and yet the sky remains silent. It's possible that life is common, and we simply have not yet looked in the right way or the right places. It's possible that life arises easily, but rarely becomes complex. Or it's possible that the emergence of life, or of thinking minds, is so improbable that even across trillions of galaxies, it has happened only a handful of times, or perhaps just once. We do not know which of these is true, but the sheer scale we've uncovered tonight changes how the question feels. When you realize how many galaxies exist and how many worlds they must contain, the idea that we are entirely alone becomes harder to accept. And yet, the silence becomes harder to explain. Every galaxy we add to the count is another vast collection of worlds where the story might have unfolded differently. Another island of possibility, glimmering in the dark, holding answers we cannot yet read. But there's a final twist in all of this, and it's the one that changes the question entirely. Everything we've discussed tonight, the 200 billion, the 2 trillion, the 93 billion light-year sphere, all of it refers only to the observable universe, only to the part we can see. But the observable universe is almost certainly not the whole universe. It is just the part from which light has had time to reach us. Beyond that horizon, the universe continues. We cannot see it. We may never be able to see it. But there is no reason to think it suddenly stops at the edge of our vision. The edge of the observable universe is not a wall. It's just the distance light has managed to travel. So how big is the whole universe? The part we can see, plus all the parts we can't? The honest answer is that we don't know, and we may never know. But we can gather clues. One of them comes from measuring the overall geometry of space itself. Space can, in principle, be curved. It could curve back on itself like the surface of an enormous sphere, in which case the universe would be finite, though without any edge, just as the surface of the Earth is finite, but has no boundary you could ever fall off. Or space could be flat, extending on and on, without ever curving back, in which case it could be infinite. When astronomers measure the geometry of the universe, using the faint afterglow of the early cosmos and the patterns of galaxies across the sky, they find that space appears to be flat as we can possibly measure, with no detectable curvature at all. A flat universe is consistent with one that goes on forever. It is also consistent with one that is finite, but simply so enormous that the curvature is far too gentle for us to detect. What this tells us is sobering. The observable universe, that 93 billion light-year sphere, with its hundreds of billions or trillions of galaxies, may be only a tiny fraction of the whole. By some estimates, everything we can possibly see amounts to only a few % of the entire universe, and quite possibly far less than that. The rest lies forever beyond our horizon, unreachable, unseeable, but almost certainly there. Some measurements and theories suggest the universe might be vastly larger than the observable portion, possibly hundreds of times larger, possibly much more than that. And some leading theories suggest something even more staggering. They suggest the universe might be infinite. Truly, genuinely infinite, extending forever in all directions, with no edge and no boundary anywhere. Think carefully about what that would mean for our question. If the universe is infinite, and if galaxies are spread throughout it the way they are spread throughout the part we can see, then the number of galaxies would not be 200 billion. It would not be 2 trillion. It would be infinite. An endless ocean of galaxies, stretching out forever, more and more of them, no matter how far you traveled, never ending, never thinning out into final emptiness. In that case, the question, how many galaxies exist, would have no number as its answer at all. The answer would simply be without end. We genuinely do not know if this is the case. We can only count what lies within our horizon, and even that count is uncertain by a factor of 10. What lies beyond, whether it's a finite but enormous space or a true infinity, is a question that may forever sit just past the reach of any telescope we could ever build. And there is something strangely beautiful in that. We have learned to count the galaxies of an entire visible universe, and in doing so, we've come face to face with the limits of what counting can ever tell us. The galaxies we can count are not scattered randomly, like grains of sand thrown across a floor. They are arranged in one of the most magnificent structures in all of nature. When astronomers map the positions of millions of galaxies across the observable universe, a pattern emerges that nobody expected. The galaxies are not spread out evenly. Instead, they gather into vast clusters and groups, and those clusters connect to one another through enormous bridges of galaxies, long, thin filaments stretching across hundreds of millions of light-years. Between these filaments lie immense empty regions called voids, vast bubbles of near-nothingness where almost no galaxies exist at all. Regions so empty that a galaxy sitting at the center of one might see only darkness in every direction. These voids are not small. The largest of them stretch across hundreds of millions of light-years of almost perfect emptiness, regions so barren that a civilization living in a galaxy near the heart of one might gaze out and see almost nothing at all, with the nearest neighboring galaxies impossibly far away. And even within the crowded filaments, the space between galaxies is staggeringly empty. Galaxies may seem packed together in images, but those images compress enormous gulfs of distance. In reality, the space between galaxies is mostly a thin, cold, near vacuum, with vast stretches of almost nothing, separating one island of stars from the next. The universe, on its largest scales, is overwhelmingly empty, with all of its galaxies, all of its trillions of stars and countless worlds, concentrated into the thin, bright threads of the web, surrounded by oceans of dark, hollow void. The whole arrangement looks uncannily like a web, or like the neurons of a brain, or like the structure of foam. Astronomers call it the cosmic web. Threads of galaxies woven around great hollow voids, all of it shaped over billions of years by the slow, patient pull of gravity. And, guided by the invisible scaffolding of dark matter beneath it all, our own galaxy is part of this web. The Milky Way belongs to a small cluster of galaxies called the Local Group, dominated by ourselves and Andromeda, and trailed by dozens of smaller dwarf galaxies orbiting around the two giants. The Local Group spans a few million light-years, which already sounds enormous. But it is merely a tiny knot within something far larger. Our Local Group is being drawn, along with thousands of other galaxy groups, toward a great concentration of mass, in a flow that astronomers have traced across hundreds of millions of light-years. When researchers mapped the motions of all the galaxies in our vast neighborhood, following the directions in which they drift, they found that we all belong to a single enormous structure, a supercluster of superclusters that they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea stretches across hundreds of millions of light-years and contains the mass of 100,000 galaxies, all of them, including us, slowly streaming toward a deep, gravitational valley at its heart. And Laniakea, vast as it is itself just one feature among countless others in the cosmic web, one immense cell in a structure that fills the entire observable universe. So, when you count galaxies, you're not counting scattered points. You're counting the lights along the threads of the largest structure in existence, a structure so big that even the entire observable universe is just a single sample of its endless, foam-like pattern. And the galaxies themselves are like glowing droplets caught in that web, gathered along its strands, clustered at its junctions, almost entirely absent from its great empty hollows. There is one more thing about counting galaxies that gives the whole question a quiet, almost melancholy depth. The number of galaxies we can see is not fixed. It is slowly changing. And in the very long run, it is shrinking. The universe is not just expanding. Its expansion is accelerating, driven by a mysterious influence that astronomers call dark energy, which we understand almost not at all. This was one of the most shocking discoveries in the history of science. For most of the 20th century, astronomers assumed that the expansion of the universe must be slowing down, gradually braked by the gravity of all the matter pulling inward. Then, near the end of the century, two teams measuring distant exploding stars found the opposite. The expansion was not slowing. It was speeding up. Something was pushing the universe apart, overwhelming the inward pull of gravity and accelerating the growth of space itself. We do not know what this dark energy is. We only know that it appears to make up the large majority of the total energy of the universe, far more than all the stars, all the galaxies, and all the dark matter combined, and that it is steadily winning the cosmic tug of war. Space is stretching faster and faster, carrying distant galaxies away from us at ever-increasing speeds. And here is the consequence. The most distant galaxies are being carried away so quickly by the stretching of space that their light is gradually losing the race to reach us. Over immense stretches of time, far into the future, more and more galaxies will cross beyond our horizon, slipping out of view forever, their light stretched into nothing, their presence fading from the observable universe entirely. In the deep future, billions upon billions of years from now, an astronomer living in our galaxy would look out and see far fewer galaxies than we can see tonight. Eventually, in the truly distant future, almost all of the other galaxies will have receded so far that their light can no longer reach us at all. The cosmic web, the filaments, the trillions of distant islands of stars, all of it would slowly vanish over the horizon, leaving only our own galaxy and its nearest companions, isolated in an ocean of darkness that appears completely empty. Future inhabitants of such a universe, with no record of what we know now, might look up and conclude, just as our ancestors did, that their galaxy is the entire universe, and that beyond it lies only void. They would have no way of knowing about the 2 trillion galaxies that once filled the sky. That ancient evidence would be gone, carried beyond reach by the relentless expansion of space. It's a strange and lonely thought. There may come a time, in the unimaginably distant future, when the true nature of the universe, the fact that it once held trillions of galaxies, becomes genuinely unknowable to anyone living then. The evidence we take for granted tonight, the faint smudges scattered across our sky, will have slipped away over the cosmic horizon, their light stretched into silence. Any thinking beings alive in that era would have no way to reconstruct the cosmos we can see so easily. They might develop the same brilliant science we have and still conclude that their galaxy is alone in an empty void, simply because the rest of the universe would have vanished from view. In a real sense, we are living during the golden age of cosmology, the era when the universe is still legible, when its history is still written across the sky for anyone patient enough to read it, which means something rather profound about the moment we live in. We exist in a privileged window of cosmic time, when the galaxies are still close enough that their light can reach us, when the universe is still full of visible neighbors, when it is still possible to look out and count them. We are living in exactly the era when the question how many galaxies exist can even be asked and partly answered. In the deep future, the evidence simply will not be there. We are among the fortunate few, in the long story of the cosmos, who get to see the universe while it is still full of light. So, let's return, at last, to the question we began with. How many galaxies exist in the universe? And now you understand why there is no simple answer, and why the journey to that answer is so much richer than any single number could be. Within the observable universe, the part we can actually see, the honest answer is a range. Somewhere between a couple 100 billion galaxies at the low end, based on measuring the true darkness of the sky, and 2 trillion or more at the high end, based on modeling all the faint galaxies hidden below our vision. We do not yet know where in that range the truth lies. And that uncertainty is not a failure. It's a frontier. It marks the exact edge of what we currently understand, the place where the next great discoveries are waiting. But beyond the observable universe, in the unknowable vastness past our horizon, the number could be far larger still. And if the universe is infinite, as some of our best theories suggest it might be, then the number of galaxies is not a number at all. It is endless. A cosmos without limit, filled forever with galaxies, more of them than any quantity could ever express. Think about the journey we've taken tonight. We started as a species that looked up and saw only a band of milky light, and believed our single galaxy was all that existed. We argued for over a century about whether the faint spirals in the sky were nearby clouds or distant island universes. We watched a single pulsing star in Andromeda settle the question and shatter the small universe forever. We pointed a telescope at a patch of empty darkness and discovered it was crowded with 3,000 galaxies. We stared deeper and found 10,000 more. We modeled the invisible and arrived at 2 trillion. We measured the darkness from the edge of the planetary system and were pulled back toward a few 100 billion. We built a new golden eye and found galaxies blazing at the very dawn of time, brighter and earlier than anyone believed was possible. And we came to understand that the true total may be forever hidden beyond a horizon we can never cross. It's worth remembering how that knowledge was won. No single person counted the galaxies. It took generations, thousands of astronomers across centuries, building telescopes, grinding mirrors, designing detectors, writing the mathematics, staring at faint specks of light for nights and years on end, arguing, checking, and correcting one another. It took someone willing to point a priceless telescope at apparent emptiness for 10 days. It took a spacecraft, sent billions of miles into the dark, repurposed to measure the faint glow of the sky. It took a golden mirror, folded up, and launched beyond the moon, unfolding in the cold to catch light that began its journey before the Earth was born. The number we're reaching for is not the achievement of one mind. It is the slow, patient work of a curious species, handing its discoveries from one generation to the next, each adding a little more light to the picture. Every step of that journey was driven by the same simple impulse that made you watch this tonight. The desire to look up and to wonder and to ask how much is really out there. And here is the thought I want to leave you with. In all of those galaxies, across that entire incomprehensible range, whether there are 200 billion or 2 trillion or an infinity of them, there is, as far as we know, only one world where a form of matter woke up, looked out across that ocean of galaxies, and began to count. That world is this one. That matter is us. We are a small species on a small planet orbiting an ordinary star, in the outer suburbs of one galaxy among hundreds of billions. And yet, from this tiny vantage point, we have managed to measure the size of the visible cosmos, to weigh its galaxies, to peer back almost to its beginning, and to ask, with real and growing precision, how many other islands of stars share this universe with us? The galaxies do not know they are being counted. The cosmic web spins on, indifferent and silent, expanding into a future where its own light will fade beyond reach. But we know. We, the counters, the wanderers, the ones who turned our eyes upward and refused to look away. So the next time you stand beneath a truly dark sky, and you find that faint grey smudge in Andromeda, remember what you're looking at. Not a flaw in the night. An entire galaxy of 1 trillion stars, one of an uncountable multitude, and one of the very few we will ever see with our own eyes before the universe carries the rest away. The number of galaxies may be 200 billion. It may be 2 trillion. It may, in the fullness of all that exists, be without end. But the act of looking up and asking, that belongs to us. And in a universe this vast, the fact that anyone is here to ask the question at all may be the rarest and most precious thing of all. Thank you for spending this time with me tonight, journeying out past the edge of our galaxy, across the cosmic web, and to the very limits of what can be counted. If this exploration gave you a new sense of wonder, please consider liking this video and subscribing to the channel. It genuinely helps more than you know, and it lets us keep reaching for the faint and distant corners of the cosmos together. And as you drift off tonight, remember that above your roof, beyond the clouds, beyond the planets and the stars of our own galaxy, there stretches an ocean of hundreds of billions of other galaxies, each one blazing with light, each one a universe of worlds. All of it real, all of it out there, right now, while you rest beneath it. Good night, and sleep well under the stars.